My seminar topic is about methods for determining polymer-polymer miscibility by thermal methods. Miscible polymer properties are similar to plasticizer polymers, which they are compatible polymers and they retain properties of each component such as toughening or reinforcement. For some examples, the miscible blends are consisting of polystyrene, polyphenol oxide, and polystyrene acrylonitrides, polymethane metaacrylates. The most common thermal analysis techniques for polymers are thermomechanical analysis, differential scanning calorimetry, differential thermal analysis, and thermogravimetric analysis. In most of the case, temperature is considered as a function of it. In thermomechanical analysis, the deformation and dimensional change of a sample as a function of temperature is measured. In differential scanning calorimetry, the heat flow to and from a sample and a reference material is measured as a function of temperature as the sample is heated or cooled, held at a constant temperature. In differential thermal analysis, measures the temperature difference between the sample and an inert reference substance, which is measured as a function of temperature. Thermogravimetric analysis measures the weight and hence the mass of a sample as a function of temperature is measured. So in such all the cases, temperature is considered as a function. Next, we are discussing about heat of mixing measurements. Calorimetry is one of the most direct methods for determining the heat released by a mixing process. Direct measurements of heat mixing of two polymers in the melt is not possible because of their viscous heating effects. However, the measurement of heat of dissolution of the blend and its component in a common solvent can be possible. By the application of Hess law, it is possible to identify the heat of mixing between the two polymers. The thermodynamic cycle used to calculate delta Hm is polymer 1 contains delta H1 and it is considered as solution 1. Polymer 2 contains delta H2 and it is the solution 2. When it is under enthalpy, it goes to 1 and 2 mixture which leads to a solution of 1 and 2. The total of delta Hm gives that delta H1 plus delta H2 plus delta H3 minus delta H4 gives delta Hm, the thermodynamic cycle. In principle, we can say that the problem of direct calorimetry of polymer-polymer mixture can be resolved by selecting a low molecular weight liquids because its molecular structure are representative portions of the polymer chains. The major difficulty lies in finding suitable low molecular weight analogs. This may not always give reliable results due to their structural difference between the polymer and analog use and the difference in their chain and end effects, steric difference and density difference. It is difficult to find a low molecular weight analogs. It is clear that the moment the distance of separation and accessibility for interaction of chemical groups are not same in all low molecular weight liquids as in polymers. This is a graph showing the heat of mixing of water in alcohol. We can see the raising of the graph. Finally, nevertheless, for a correlation has a number of systems been found between a relative good polymer-polymer miscibility and the sign of the heat of mixing of their low molecular weight analogs. It is clear that heat of mixing may be only possible in low molecular weight analogs. And thank you.